Hi guys, welcome back. um, we're going to be looking at today is we're going to look at the Bose Einstein condensate. So I'm actually going to pull up a screen right here for you guys so we can take a look. And so what the Bose Einstein condensate does is it gives us another form of matter, which is really pretty amazing. So generally, I mean, we know of four forms of matter. I mean, we know of solid, liquid, gas, and plasma. And if you don't know what plasma is, we could kind of take a look. You would notice in here, this is where the plasma would be here. So we're kind of seeing charged particles here. And plasma is really signified by a very high temperature that allows pretty much the state of the matter to break down into charged particles, and those charged particles are conductive and they are susceptible to magnetic fields. So that's really an overall view of what a plasma is. And you'll notice here lightning. Lightning's an example of a plasma. Another one would be obviously the sun. And then from there, effects from the sun, which are the aurora borealis is an effect where we can see a plasma storm. So we kind of have a picture of aurora borealis here. If we can come down, so here's the northern lights here. Really a great picture that came out of Jess Thomas's article on Newsweek. So I really wanted to bring that article in here. But what is this? What is this Bose-Einstein condensate, and how does that form of matter? And it really goes the opposite way of the plasma. So it really goes. It's really going to go backwards here on the solid, and it's going to bring the atoms close to absolute zero. And this was originally proposed. Let me just come down a little bit here. Well, actually, I'll go to him. And so let me go over here. And this was originally proposed by, I'm probably going to say his name a little wrong, but Satyendra Nath Bose. Now, that word Bose may sound familiar because we get fermions and bosons. And the bosons are, the non that are not the fundamental particles, and it's actually named after him. He's considered, India's Einstein. And there's a little article here on him, and this was celebrating in 2025 his 130th birthday, and so I guess that's going to be that would be January 1st, because it says on the first day of the year 2025, it's his 120th birthday. This article was written in December 31st, 2024. And it gives a little description of him here. This here is on Lycodon. I found it on Lycodon, but it just tells you a little bit about him, and it says that he was an Indian physicist and mathematician whose name is given to nearly half of the universe of atomic particles, including the elusive God particle, the Higgs boson. In fact, the word boson is derived from S.N. Bose's name and refers to the subatomic particle that occupies half the universe. The other half is occupied by fermions. But anyways, it says early in the 1920s, Bose collaborated with Albert Einstein in the field of quantum mechanics to develop the Bose-Einstein statistics and the theory of the Bose-Einstein condensate. Credit goes to a large heartedness of Einstein for acknowledging the greater contribution of the Indian physicist and for putting his own name after that of Bose in that regard. Einstein would have it published in a German German scientific sorry, I'm like losing my mind here. A periodical, a German scientific periodical. So I just we'll go there real quick and just take a quick look there. and that's way down here. And it was the I'm probably going to say this wrong too. So Zekret for physics. So it's written right here and stuff. But Einstein, when he would read what Nath Boss had sent him, he would immediately realize the significance of it and have it published. And then he would work with he then would correspond and work with Boss. So let's talk about this now and talk about how it comes about. So the Bose-Einstein condensate occurs near absolute zero. Okay. During a super chilled phase, the atoms possess very little energy and start to aggregate. So thinking about aggregate, thinking about how materials kind of come together. It's really how the atoms are coming together and they're forming a new state. Because they basically act in unison as one atom. The viability of the Bose-Einstein condensate would not come until around 1995. It was proposed theoretically, and it kind of made sense, but proving it experimentally, it would take lasers. And the idea of the laser, and it might seem funny that you're actually going to introduce light particles into a gas in order to cool it down. But actually, what light does when photons are particles, and when they hit atoms on that level, they actually form collisions, and they actually tend to slow down the atoms. So, in order to form that that Bose-Einstein condensate, scientists used rubidium atoms. And then what they did is they used lasers to, like I said, to slow them down. And this happens, here it is, it's explained a little bit, because the laser light actually pushes on the atoms, causing them to slow down. Then what happens is once the atoms are slowed down enough, an evaporative cooling method is used. This was explained by NASA. It was something I found pretty neat. That they actually, what they do is they form a trap, which is a magnetic field that takes the rubidium atoms that have a specific threshold energy, and it holds them in it. And all atoms that are a little more high energy are able to escape this magnetic field and just go off. So this is how they're actually cooling it more. And once they get it to that point, where they got rid of the more energetic atoms, and now they just have these rubidium atoms that are really now close to absolute zero. They can even cool it further by weakening the magnetic field, according to NASA, and that allows an adiabatic expansion to take place, where the atoms get further apart from each other and they even get colder. This is a picture here that I took off of one of the videos and stuff, which is just an animated view of the laser light coming in, and but basically it's the particles, it's the photons that are causing collisions with these atoms, and it's causing them to push on them or to slow them down. Now, Eric Cornell and Carl Weinman used rubidium atoms to show the Bose-Einstein condensate effect in 1995. And then there was this other German physicist, Wolfgang Kitterles. He would do it with sodium atoms the same year. So Eric and Carl uses rubidium, and then Wolfgang Kitterles comes along the same year and he uses sodium atoms, and they both show the Bose-Einstein condensate. In 2001, they received the Nobel Prize in Physics for their work. Okay. Now, finally, so what? How important is this? Like this new, this new matter that's really forming here. That that the atoms are really, um, they're pulling together, and you can see right here, and they're acting as a single atom, which is giving us another state of matter. But what is this really helping us with? And one thing that scientists found, and I've got that kind of over here, if you can just give me a brief moment. Um, this theory really works with, well, theory, it's more than a theory now, but it works with quantum entanglement, which we kind of talked in the past in another video about that. And that quantum entanglement works obviously with quantum computing. And it also improves MRIs, and it works with improving navigation. And then finally, one of the most recent discoveries in physics was detecting gravitational waves. So it took us a long time to get here. Originally, this was Bose was working on this in Einstein in the 1920s. And it takes till 1995 for it actually to be shown that, that this fit state of matter actually exists, where these atoms come together and they act as one atom. But that leads to other things, and it's leading, it's been leading to improving MRIs. But most important of all, pushing the science forward by detecting gravitational waves, and now getting into quantum computing, which is only going to go on from there. So it was really enjoyable learning a lot about this, and it was nice also watching. I watched a few videos on these as well, and I've got some sources down here, and NASA's Jet Propulsion Laboratory, a recipe for cooling atoms to absolute zero. It's really a nice video. Princeton's Plasma Physics Laboratory, there's a video there. And the Bose Einstein Condensate explained in simple words. And then I also like Thomas Jess's Newsweek article on dark plasma eruption aurora forecast. So it was a lot of fun looking at this, and and learning more, about the Bose Einstein concept. Sorry, but it was enjoyable. So thanks, guys. That's about all tonight. And have a good week now. Bye now.